In this situation, we're going to have a track and a box with masses. So we'll call this mass. You're going to have a string, and you're going to have a sensor pulling on that string horizontally. So this has to be horizontal. If you draw a free body diagram of this situation, you're going to have tension and then friction between the bottom of that box, right, and the track. You'll have normal force and you will have weight. When we write out Newton's second law, you're going to have Ft minus Ff equals max, and Fn minus Fg equals may. So we've done that a whole bunch of times by now. This is our positive direction. Now, when we're dealing with static friction, right, when this Ff is Ff sub s, then we know that mu static times normal force is how we calculate it. We also know that it cannot be moving. The whole point is that it's static. It hasn't yet moved. You're pulling, but it hasn't resulted in motion. Okay? And what'll happen is on the force time graph, right, when you're pulling with the sensor, this is going to be the force that you're pulling with the sensor. So this is actually your tension force, and we're going to do it versus time. So this will be on capstone, and I'll show you this. You're going to get a graph that goes like this. It's going to go like this. Increase, increase it. It's going to get bigger and bigger. Probably not going to be that smooth, but it'll get bigger and bigger to a maximum. Right here, we call this point the break-free point. This is the point of maximum static friction. This is the point we need in order to figure out what static friction is. Okay, what static friction force is. So we want that maximum. So then, if we want to look at these relationships, well, since acceleration is 0, right, it's not moving yet, the tension force is equal to the friction force, and the normal force is equal to the weight of the object. So once we get the tension force, we know that's our friction force. Normal force is equal to the weight of this system. So you can calculate weight by doing mass times gravity, right? So this is going to be the weight, the mass of the system. And this is, as usual, just 9.8 meters per second squared. So you're going to need to figure out what the weight of the system is by doing mass times gravity, and then that'll give you your normal force. So if you look at this equation, right, theoretically, how are we going to find this coefficient? So for that, and this is our theoretical derivation, right, this becomes the slope of a graph of friction versus normal force. So if I put friction force here and I put normal force here, then this must be the slope. So you need several data points, of course, to measure it, but the slope is going to equal the coefficient of friction. So we're going to need to do this a bunch of different times, right? This experiment, pull a bunch of different masses, at least 5, so that we can get 5 different values for this maximum static friction force so that we can plot 5 different points. So you're going to do 5 data points, 3 trials each, as always, right? And you're going to measure the maximum value of the force from the F versus T graph. Okay? Each data point is a different mass. We're controlling this normal force. This is our dependent variable, and that relies on weight, and weight relies on mass. So the different data points, right, this is going to be 5 different masses. Right? So this has to change. And you don't want to change it by a little. We're going to change this by a lot each time. This should be fairly significant. So we're going to be using those mass bars, which are pretty heavy. So then how do we find the kinetic friction force? So kinetic friction force, we're not changing very much here. What's going to change? Well, the free body diagram doesn't change. It's still tension, friction, normal, and weight. Therefore, our Newton's second law equations don't change. This does, though. What we're going to do instead, for kinetic friction, we know that FFK equals mu K times Fn. So this relationship is almost identical, but it has to be moving. It can't be at rest. But we still want to make acceleration 0. So how can we be moving and have acceleration be 0? Well, we can say that it's going to move to the right, but let's make acceleration 0, so we have to pull with constant speed. If we pull with constant speed, then this relationship still remains the same because acceleration is 0 on both axes, right? So when we get what it's going to look like is, let me draw this in red. After this point, right, once we pull, and then it's going to break free, it's going to suddenly start moving, and then you are to move at constant speed. When you move at constant speed, you should get a roughly horizontal line. This region here is when you're pulling with constant speed. And this is going to be where you have an average FFK. This is where you're going to have kinetic friction because you're moving, but you're moving with constant speed. So that's that part of it. So what's going to happen then? You're going to do 5 data points with, right, 5 different masses, 3 trials each, and you're going to measure the average value of the force from the F versus T graph. Now, you're not going to do this separately. This is going to happen simultaneously. You're going to get one graph, and you'll be able to pull both of those pieces of information off of the graph. So you need a data table that will enable you to measure all of that and record all these observations. So what do we need? Well, we definitely need to include the mass, right? The total mass being pulled, and that'll be in kilograms. So these are going to be your different data points. And then we're going to need our maximum tension force in newtons, and we're going to do that 3 times. Trial 1, trial 2, trial 3. And then we're going to need our average tension force in newtons. And again, we're going to do trial 1, 2, and 3. And that's going to be your data collection. Now, what are you going to need to do for your analysis? Well, we've kind of already outlined it here. We have to be able to calculate the weight so that we can get the normal force. So that's important. So we need a column for weight, and then we're going to need a column for normal force in newtons. So how do you do that? Well, put in a formula for that. We know that this is mass times gravity. Well, don't type mass and gravity. Type, right, you're going to click on this cell and then times 9.8 and fill that down for your 5 different data points, right? You're going to have 1, 2, 3, 4, and 5. So these are going to be your 5 different masses. So that's going to be in there. This is equal to that. So those columns will be exactly the same. All right, so we finished that part, which is going to be our x-axis. This is now going to be our independent variable that's going to be graphed. And then we're going to need a column for our friction force, because that's what we need here. So friction is equal to tension. So we need to have our friction, and we'll call this our static friction force. Our static friction force is going to be the average of these tensions. So you can do your average maximum tension force. Now you know how to do formula for average, right? You type the word average and then highlight these 3 cells so you can get the average tension force because it's the same as your friction force. Then we need our kinetic friction force. That's going to be the average of these trials. Average of your average tension force. So you're going to take the averages of those 3. Fill that down, right? So once you put in these formulas, then you'll be able to set up your graph. We're going to have one graph, normal here, and we're going to have friction on the y-axis, but we're going to make 2 lines. We're going to have one line for our kinetic friction, and we're going to have another line for our static friction. And I'll show you how to do that when you're done.